All right, let's start. A warm welcome, everyone, to our second calcbond webinar, which is about the Analytical Toolbox and the Design Explorer of the Analytical Toolbox. I'm Axel. Next to me is Fabian.
Hi, welcome.
And let's go into that. First of all, we have an announcement. You know that from the last time, for those who have been there last time as well, keep your microphone muted and keep your camera switched off. That's easier for us to handle all this. Cool, thanks a lot. So what's about the agenda today? We have a brief introduction about AR engineers and about Fabian and myself. And then we briefly introduce the platform, of course, calcbond, which is about the Analytical Toolbox, Auto FEA, material cards, and the wiki, and so on. We give you a brief little detour. The detailed presentation of the Analytical Toolbox and design exploration will be done by Fabian. He will show you about the available configurations, about the calculation capabilities, and of course, results and reporting. And then after that, we give you an outlook about what's coming up within the next year or so, upcoming features, and so on. And finally, we have 15 minutes planned for Q&A, which we ask you to do via the chat. All right. So let's start. As I said, I'm Axel. I'm the CEO of AR Engineers. I founded the company in 2010 with the focus on composite design of structures with FEA, of course. Production supervision we have today. We have some research and development projects, of course, and as you can see within calcbond, that we develop software originally internally for ourselves to do FEA in a better way, but now we apparently have a platform running online. So software is definitely a part of us. All right, maybe a few words from Fabian.
Yeah, thanks, Axel. So my name is Fabian Nowacki. I serve as the head of the engineering team here at the company. I'm an aeronautical engineer myself, have been with the company for 7.5 years, roughly, and I coordinate the industry and R&D projects, and I'm responsible for the technical development of the calcbond platform and will be guiding you through the Analytical Toolbox feature later in this webinar today.
All right, and if you're interested in a one-on-one meeting with Fabian and or myself, just use the barcode and schedule a meeting with us. We would look forward to that. Thanks a lot. All right, so let's dive into the platform. What is our mission? Our mission is to simplify the use of adhesives by providing a reliable solution for adhesive bonded joint calculations and adhesive bonded joint in general, adhesive bonded joint design. So that includes 3 different main areas for us, which is at first the database of adhesive materials and the knowledge about adhesive, which we provide within our wiki. Secondly, it's the Analytical Toolbox. We speak about that today. Fabian will give us a tour through the platform, and of course the automated FEA. We had the Auto FEA webinar a month ago, and we provide a recording of that in our YouTube channel. You can go on the YouTube calcbond channel and you'll find the recording there. All right, so let's move on.
Before we go into the live demonstration, just a brief introduction about the Analytical Toolbox itself. This is the first calculation feature, basically, or the basic calculation feature of calcbond. And let me give you some brief preliminary information. So in general, the question is, of course, how can I calculate adhesive joints? If you've been with us with the first webinar a month ago, you know that there are numerical simulation possibilities using the finite element method. But before that, you can also use basic hand calculations or advanced analytical formulas, which represent closed mathematical solutions for very specific cases. So this is possible for any general structure, but also for adhesive joints. And there you can calculate your adherent and adhesive layer performance, for example, in terms of strains and stresses acting under mechanical loading or also other loads. And these always come with simplification assumptions. So you have a natural limitation of the applicability of these formulas, but for these certain cases, they can provide direct results, basically, based on the math behind that. But because the governing equations and the problem in reality is very complex, you need to define a set of simplifications that you work with. And when you know these, then you can very effectively work with these formulas. And the benefit is clear. These methods are fast, they're easy to implement, programming-wise also, and they come at a very low computational cost compared to numerical simulation, for example. So these methods are perfect for preliminary design in your early project phase when dealing with adhesive joints. And that is why we have included some of these tools also inside calcbond, and that we will show you in a minute. So let us go online and try it out.
Perfect. Thanks a lot, Fabian.
So I will just quickly change my setup here, and then we can move on into the live presentation. So now you should be able to see
Nice. All right.
the platform here.
So when you go on www.calcbond.com, you'll see this first landing page, and we don't want to go into detail with registering. You'll find as well on our YouTube channel as a very short, brief introduction about how you register. It's very straightforward, just 1 or 2 minutes video, and it's very straightforward. Sometimes it happens that it's because it's a double opt-in that you get an email that you have to confirm your email address, and sometimes this will get caught by the spam filter or your local servers. So make sure you get that email, or send us an email that something didn't work, and we help you out. And in the moment you have registered, you'll be in a free trial, and you will start from that index page here. In the middle, you see at the moment an overview about some basic information, some videos that will just explain the platform itself in depth, and some recent activities that we present further down. If you registered and you turned on the newsletter checkbox, you'll get, of course, you get monthly updated with our latest and recent activities anyway. So yeah, and then on the left-hand side, we have our navigation bar. In the top of the bar, you see the Analytical Toolbox, which will be presented by Fabian in a minute. The Audio FEA, as I said, was presented a month ago. Recording is online on our YouTube channel. Check that out. It's very interesting. And then material cards is a very cool chapter with material cards from Kissling, Zeker, Huntsman, and IPS adhesives at the moment. 21 different material cards are online. You can go through all the material cards. Even if you don't do calculations, you have all the information that are necessary in these material cards, and a contact person from that brand to get in touch with them directly. The self-calculation area displays all your calculations that you have done and saved. For the Analytical Toolbox, Fabian will leave some words about that. You have to actively save calculations. Audio FEA saves every calculation automatically, and you have to delete them actively. So everything that you have calculated will be there. And some other interesting area is the Wikipedia, our calcbond wiki. That's very interesting for those people who'd like to study about adhesive joint design or adhesives. There's a lot of stuff about the platform, of course, and about how to handle the platform, how to handle adhesive joint design. Very interesting to get into the topic, or if you're already in the topic, to move further into calculations and how to set it up. Going back to the platform, I think the user portal is interesting as well, because there you see all your information that you have entered when you have registered for a free trial for the platform. You can change them here by editing on the left-hand side. On the right-hand side, you see in what subscription plan you are. So whether you're free or pro, and you see what cost would come up if you become a pro, or if you want to top up because you have used all your FEA tokens down, you could top up and get some extra calculation power. That's on the user portal side. I think all the rest, if you go further down, there's some legal information about terms and conditions and so on, not too important for the moment. So I would hand over to Fabian and let's go into the analytical toolbox.
Thank you very much, Axel. So today we want to look deeper into the analytical calculation capabilities in calcbond. And as I explained earlier already, these are mathematical formulas to solve for specific cases of adhesive joints. And a very common bonding case is a single lap joint with two rectangular plates bonded together, basically. And as you can see here in these three different configurations, we have provided the typical lap shear specimen, so to speak, in the middle, but you could also go for a more generalized single lap joint. So it is kind of an adhesive adherent sandwich with custom capabilities of adding the different section forces and moments if you want to dive deeper into your specific loading scenario. You can also select the typical lap, single lap shear specimen. You can either calculate it as a lap shear specimen, or also, if you want to, you could enter transverse or forces or moments, which will then switch the boundary conditions automatically to come up with an equilibrium for these reaction forces on the other side of the adherent. Or, for example, the double L bracket we have also as a specific configuration. If you have these kinds of profiles bonded together, for example, so that simplifies your workflow a little bit. So in this demo today, I want to show you the possibilities using the typical lap shear geometry here. So scrolling down, we have the user interface with the different input boxes considering the adhesive joint definition. So on the upper side, we have the data entry for the adherent materials. So on the left, top left box here, we have adherent 1, which would be the upper adherent in this drawing here. On the right-hand side, we have the second adherent, so the one on the bottom. And for both adherents, you can define an isotropic material from a predefined list of engineering materials that we have available in calcbond, different steel, aluminum alloys, plastics, titanium, glass also. So you can select one of these, and you can also select a user-defined material where you would be able to enter your own engineering data. In this case, for the analytical calculations, it's quite simple. You have the Young's modulus, you have your Poisson ratio, and then, of course, you have the thickness of your adherent itself. You could also define a simple composite layup. So if you have an orthotropic adherent, you could define your laminate stack up, and then calcbond would calculate the effective stiffness parameters that have an influence on the calculation results. But in this case, let's stay with the simple isotropic materials. Let's set up a symmetrical joint with steel alloy 3 millimeters in thickness on both sides. And in the middle, we have the adhesive selection. So here we have a drop-down list with predefined engineering data for manufacturer-specific products provided inside the calcbond material database. But again here, so if we select products, we can see the different engineering data being put inside the fields here. Or again, I could also define my own custom data. And again, this is simple properties like the Young's modulus, tensile strength, compressive strength, and the layer thickness, of course. So let's say I want to calculate with an adhesive layer thickness of 0.5 millimeters and take these generic values basically for my user-defined input. Then on the bottom left-hand side in the box is the geometry. I want to define a joint width of, let's say, 25 millimeters, an overlap length of maybe 15, and I will keep the free lengths of the adherents symmetrical. And then let's say I want to transfer a load of up to 5 kilonewtons. I can then calculate the stresses by clicking on the blue button. And within a snap of a finger, basically, I get my results back inside the platform. So here I have an overview of the acting member forces, of the material properties of my joint definition. And scrolling further down, I have my adhesive stress results. So in this case, what is important to note is that the analytical formulas go beyond the simple assumption of an average shear stress being distributed in this type of specimen, because they calculate a differential shear stress distribution along the bond line. So we have these coordinates going from 0 to 1, representing the left edge of the bond line towards the right edge. And we see the green line here, we have a variation in the shear stress with peaks reaching their maximum at the free edges of the bond line. And also we have peel stresses acting in terms or induced by moments as a result of the asymmetrical load introduction for the thickness offset of the joints. And these stress components are calculated inside the adhesive layer, basically, and then are transferred into a failure criterion, which we see here in the box on the right. So this basically predicts the cohesive failure of the adhesive layer itself. We do not calculate any interface behavior in calcbond because it is basically not yet really possible to define formulas for that. But for the cohesive failure, there are different methods where it's possible to roughly predict the expected failure threshold. And for this, we have so-called equivalent stress approaches. So we have a set of different equivalent stress models like the von Mises three-dimensional equivalent stress, Drucker-Prager, Tresca, which are differently suitable for different types of adhesives. And if you want to learn more about that, you can take a look into the wiki or just give us a call also, and we are happy to explain more about that. But as you see here, maybe let's stick with the von Mises stress. You can see the green curve represents the distribution of the equivalent stress compared to the tensile strength of the adhesive material in this case. And here we see the red straight line basically would represent our limit threshold. So if we, I don't want to do the 10, let's do the 1. So in this case, I have set my inverse reserve limit to 1.0, meaning that if I go beyond this value of 1, I have exceeded 100% of the stress capacity, so to speak, of my adhesive. So if you divide the occurring yield stress by the allowable tensile strength, you would reach a value between 0 and 1 if you are still within the safety range. If you go beyond that strength, you would exceed the value of 1. So if you want to have more safety incorporated, you could, for example, enter an IRF limit of 0.5, which would give you a safety factor of 2. And then you can see, okay, my stresses exceed this limit in a larger area of the bond line, basically. And if you want to conduct a similar calculation, but don't want to enter all the data again, you can click on the Transfer to New Calculation button here. And then you get a new setup with all the previous information saved. And then you can just do some small adjustments. So let's say we want to change the first adherent to an aluminum alloy. Maybe we want to change the thickness. Let me do that again. Yes. So we have the steel alloy as the adherent material on the right with 3 millimeters thickness, and we have 4 millimeter thickness on the left with aluminum. So we have an asymmetrical joint configuration, and I'm keeping the forces as they were. And if I calculate again now, I can see a slight asymmetrical distribution of the stresses. Maybe I can give it even a little bigger push just to make it more clear. Yes, so this would be an extreme example of a very thin bond line and largely different stiffnesses of the adherents. And then we can see how they influence the asymmetrical distribution of the stresses within the adhesive layer. So this is a very powerful or a very strong capability of the calcbond analytical tool, that you get to learn about these influences of your design parameters on the adhesive layer strength performance. And if you want to go a step further, and let's say perform a design study where you have a large design space and want to quickly investigate how different parameter variations influence your joint performance, you don't have to do 100 or 500 different calculations manually yourself. You can use the design space exploration feature, which is in the box below your transfer to new calculation button. And here you can select different variables. We have, for example, adhesive materials, so you could select different products to compare the different mechanical properties. And then you would click Explore for the given configuration that you have calculated before. And then you get this overview here. So in this matrix, you have the top left and the top right as a result interface, just the way you saw it before. But on the bottom, you have two new boxes, and these boxes show you the comparison of the different variations. In this case, we have discrete variables, so we have 5 different products that we can compare. And if I switch through the bars here at the bottom, or the tabs, I can see the bar charts changing, highlighting whichever parameter I'm looking at right now. And if you look at the top left and the top right graphs, you can see how these dynamically change in between your design parameters. So here you can have a direct comparison and see how they in a different way affect the stress distribution. So this would be for different types of adhesives, but maybe I want to see, okay, what does my joint length, so the bond line length, have as an influence? Let's say I want to calculate from 0.3 millimeters to, sorry, not thickness, that's a bit short. Let's say I have 15 millimeters in the length up to 150. Click on Explore. And now I have the same thing, but now I have a continuous design space, so I can move this slider here from my bottom limit, 15 millimeters of joint length, up to 150. And here I can see on the top how the stress distribution varies. And I can also see that the maximum values do not really change that much. So that's also a very interesting learning, which actually proves itself in practice, that you don't need to extend your joint length infinitely to improve the strength, but there are other measures that are more effective to improve joint strength. And that is how you can find it out, by using this Design Space Explorer. Yeah. And if you want to have one design, you can apply it, get your normal result illustration here. And then if you want to save your calculation, you can do so in the bottom left, where you can save your result, let's say webinar demo 1. Then you can save the calculation and it'll be saved in your user account in calcbond. So you have the analytical calculations table, and on the bottom here from today, from the webinar, you can have your demo project. You can click on the pencil and change the name if you want to. You see the date, and you can request your PDF report. You can do it here, or you can also do it inside the calculation object. So going down to the bottom, on the right-hand side, we have the Generate PDF Report box with this blue button. And once it's clicked, an automatically generated PDF document will be made available for you, which you can view in your browser, or you can save offline, of course. And it's nicely laid out with the cover page, all the important information, an interactive table of contents, so you can jump to the different chapters. And here you have an overview of your joint configuration, the loads, the material data. In this case, we have a generic 2-component epoxy with default values, but you would also be able to have manufacturer-specific properties listed here with a link to the products. And then you have your result plots of your analytical calculation, in this case, which you've seen online, with some more explanation text for you as a help to understand how to interpret these results in terms of the analytical calculation methods. The same with the inverse reserve factor, so the equivalent stress approaches as a strength prediction. table as a summary. So in this case, we would exceed the expected tensile strength. That is why you have the red values above 1.0 here, because you have the allowable IRF of 0.5. So if you would say you have values between 0.5 and 1, they would also be red in this case. Yeah, and then after some general information text blocks, on the last page on the back matter, you have some important links toward the platform. You can go to the wiki, to calcbond directly. You have a unique calculation ID, which is saved inside the database. So here you have a QR code available and also a digital link, which sends you back to calcbond to this specific calculation object, which you can also share with colleagues. So if they're registered in calcbond, they can click on the link and access this calculation object directly or scan it via their smartphone or tablet, for example. Okay, so yeah, that's it about the analytical toolbox in brief summary. And moving back to the presentation, I want to show you some more developments coming up in a second. So let me share the screen again. And now moving on, we want to know what's coming up in calcbond further down the road this year. The first big feature extension will be the material cards database, as in terms of, now you should be able to see it, sorry for that, in terms of user-defined material cards. So in addition to the manufacturer-specific product being listed inside the calcbond database, you as a user will be able to enter and save your own tested values independent of the default material data in calcbond, and you can manage it inside your own account and also share it with colleagues inside your organization or also with people outside your organization if they are registered calcbond users. And you always have full control over who has access to the data and who can manipulate it also. Another big feature is the 3D interactive result interface. So here you have a more interactive three-dimensional interface inside the AutoFEA module where you will be able to view your model in 3D, show and hide different components, move and rotate everything, zoom into them to get a more detailed analysis, have extended result types available, more different failure criteria for the adhesive layer assessment. And also, if you're more familiar with stress analysis, you'll be able to enter your custom result criteria and display them the way you want them, basically, and make them available for your own PDF report. And finally, similar to the design exploration in the analytical feature, we also want to provide this for more complex joint geometries in 3D based on FEA, but also going beyond classical FEA with, for example, machine learning-based algorithms. And this will provide you with responsive real-time design calculations and parameter studies, basically. So you will be able to study a large amount in a very short time and therefore get a very large boost in efficiency to reach early on project decisions with minimum effort, basically. Okay, that's it from me so far. Now giving back to Axel.
Thank you a lot, Fabian. I personally believe the Analytical Toolbox, as well as especially the Design Explorer, is a very powerful tool within calcbond, and that leads me straight to the subscription plan. It is at the moment for free, so you can use the Analytical Toolbox as much as you want. Only for the Design Explorer or the AutoFEA, you will have to move to Pro. So yeah, and here you go. That's for those who haven't registered as a user now, haven't maybe seen this table yet. As a free user, you'll be able to run the analytical stress calculation for single lap joints, and you get the tabular stress results from the toolbox, of course, and you get the material cards. For the rest, you will have to become a pro, or when you haven't registered yet, in the first free trial, you will see as well the entire platform. You will be able to test the AutoFEA module with reporting and so on for in 5 times basically. And if you enter the promo code and you're interested in getting a license for a year, like 12 months, we're happy to give you a discount for this package and provide that for 3,000 euros. Of course, if you need some training for the platform with the platform and joint calculation, let us know. We have a package for that as well. All right. So yeah, if you have questions, feel free to ask. If you're interested in a one-on-one meeting with Fabian or myself, just send us an email, scan the code, and request a meeting. And as well on the next page, yeah, probably maybe you want to.
Yeah. So a small announcement into the future. We will be having another webinar in April this time. So in approximately 2 months from now, on the 18th of April at 4 p.m. CET again, we will be having a webinar about the material cards. So the material database inside calcbond with the manufacturer-specific products will be shown by us, showcased and explained. And there you will also learn which data is available and how you can work with it in terms of calculation. So yeah, save the date. We'll distribute this also via our newsletter and in online posts. Thursday, 18th of April, 16 or 4 p.m. CET.
Perfect. Yeah. So thanks for being with us in the second webinar of calcbond. And now, if you have questions, please let us know and type them in the chat.
Yeah. Perfect. Thank you very much. Okay, we have the first question from Sarah or Zara. How do you take into account different adhesion properties due to pre-treatment? Yes, that's a good question. I've mentioned during the webinar that with the analytical toolbox, it's not able to calculate the adhesion behavior, basically, because it's a very complex concept, or the phenomena are very complex. What we do provide, which is given inside the wiki as well as the material data for some different product types, are recommendations in terms of which type of pre-treatment, surface pre-treatment needs to be done for different substrates with the certain adhesive that you are looking at. So if you have one specific adhesive that you want to look at inside calcbond in the material database, then you will get recommendations in terms of the surface pretreatment and substrate compatibility. However, moving further, it is not possible to take into account the different pretreatment different cases, so to speak, in the calculation, because the analytical modules are only looking at the cohesive performance, basically. So yeah, I hope that helped to answer your question, Sarah.
All right. I think we can leave it here. Yeah, so thanks a lot from my side for being with us in our second webinar. And we are looking forward to seeing you in the third one, as Fabian announced in mid-April about material cards. And we look forward to seeing you again.
Yeah, thank you very much. And take care and enjoy the rest of your day.
Perfect.
So, see you soon.
See you.
Bye-bye.
Bye-bye.